am still in section 5.2, and the next problem I would like to look at is the following. A table of values of an increasing function f is shown. Use the table to find lower and upper estimates for the integral from 10 to 30 for f of x dx. And we're asked to use 5 equal subintervals. So if you take a close look at the little table of values that are provided, we can see very clearly that this is going to be an increasing function. You see, as we move from left to right, our function values get bigger. So when this is the case, if we're dealing with a strictly or a monotonically increasing function, the lower estimate is going to be the same thing as the left Riemann sum. So for this problem, let's go ahead and calculate the lower estimate, or in other words, the left Riemann sum. So here I will have L sub 5, again the left Riemann sum with n equal to 5. Again, by definition, this is going to be delta x times, and this will be the function evaluated at 10, at 14, 18, 22, and 26. So these values specifically are, again, we need to say what delta x is. You can see that the width of each subinterval is going to be 4. So this will be 4 times. And now we can simply just consult our table for these function values. F of 10 is equal to negative 12, negative 6, negative 1, 2, and 3. All right, go ahead and calculate. When I stick this in my calculator, I get negative 56. All right, so let's repeat the process, but this time just with a right Riemann sum. So R sub 5 will be delta x times, and this time if you look at the right endpoint for each interval, we will start with the function being evaluated at 14. So f of 14, f of 18, 22, 26, and 30. And again, these values specifically are going to be 4 times f of 14. So we have negative 6 plus negative 1 plus 2 plus 3 plus 8. And again, I will use my calculator to calculate here, and I get 24. So you see the left-hand Riemann sum, in other words, the lower estimate here is negative 56. The upper estimate will be 24. Now, I would like to just put in one note here. The reason why we were able to equate the lower estimate to either a left or right Riemann is because my function was monotonic. That means always increasing or always decreasing. In the event that you deal with a function that both increases and decreases on your interval of interest, you would need to consider each interval individually and decide where the function reaches either its min or its max. All right, let's take a look at another problem. The next problem says evaluate the integral by interpreting it in terms of areas. And we would like to find the integral that goes from negative 9 to 0 of 2 plus the square root of 81 minus x squared. Now, it may not immediately look like that to you, but this is actually a very nice geometrical shape for which we know the formulas for area. All right, so let's just quickly consider the square root of 81 minus x squared. So this is my function y. If I were to square both sides, we will get that y squared is equal to 81 minus x squared. And if I rearrange this equation, I will get that x squared plus y squared is equal to 9 squared. And maybe now you recognize that this is in fact the equation for a circle. X squared plus y squared equals the radius squared. All right. All right, so I would like to go ahead and graph this for myself. And I actually drew this graph for us. So this is what the graph of this particular circle looks like. All right, but now keep in mind that our function that we're actually working with is not y equals the square root of 81 minus x squared, but it is in fact y equals 2 plus the square root of 81 minus x squared. So we need to add 2 to that function. And we know what happens when you add a constant to a function. It is going to cause that graph to move up by that many units. All right, so now let's see if we can geometrically find this area. So I would like to shade 2 regions here. The first is that of the circle, and I'm going to kind of just try and kind of with my highlighter kind of highlight. So this is the first region. We know how to find the area for half a circle. And then the other piece of the region that we need to consider is going to be just like this rectangular region underneath. So all of this together is going to form all of the area under. All right. So first of all, for the semicircle, we know that area is equal to, so for a regular circle, it is pi r squared. So in this case, it is going to be half pi r squared. All right. But be really, really careful. Let's quickly just look back at our problem. One more thing is that we need to keep in consideration. We are really only evaluating this integral from -9 to 0. So maybe I should come back here and kind of just shade again. So instead of shading everything here, I really should only be shading this region, right? So we're actually only working with a quarter of the circle for this problem. And then the same thing for that rectangle. We're only working in this region from -9 to 0. So really we only need the area for a quarter of a circle. So that will be 1/4 pi r squared. So let's see, that will be equal to 1/4 times pi. And again, my radius here is 9. 9 squared is 81. All right, so let's just write this as, I'm going to write it as 81/4 times pi. All right, and we also need to find the area for the little rectangle at the bottom. So that area is going to be 9 by 2. So this is equal to 18. So my final answer here is going to be 18 plus 81 pi over 4. And if you would like, you can plug this in your calculator to get the rounded or estimate value. But your homework will also accept and actually appreciate exact values. So you can type it the same way that I have it in here. All right. I hope that these few hints